In this video, we'll look at good digital practice techniques when using breadboards in our digital logic design laboratory. When we talk about a breadboard, we actually mean a solderless breadboard. That allows us to wire components together without having to solder the wires together. If we look at this example of a breadboard, it shows vertical columns and horizontal rows. The vertical columns on the left and on the right are used for the power bus. The red side is typically used for power, and the blue side is typically used for ground. These columns are short-circuited together, so each of these holes here would be connected together as though they were wired with one conductor. These rows are typically called our component bus. This is where we'll put components, resistors, or integrated circuits. Note, however, here, if we have the red power bus on the outside of this column and the red power bus on the inside column here, these two are not connected together. So the sides are not connected. We'd have to connect them separately. And we'd have to do something to actually connect power, 5 volts here, and connect ground to this column. If we did that, all these holes here would be connected to ground. All these holes would be connected to 5 volts. However, this side will not be connected unless we do something to connect them. So how we could connect them, for example, is to just run typically a red wire from power to power, a black wire from ground to ground. Sometimes the breadboards have a positive label showing that this is your positive voltage and a negative label for the negative side of the voltage, and sometimes they don't. So behind this breadboard is where the magic occurs. If we look at the columns, what we have is one big thick line of metal, some conductive material that allows us to connect so that all these holes are in fact a short circuit. So it's vertical in the columns connection, and in the component bus area, these metal blocks are horizontal columns. What the pins themselves are just little tight connectors. So when you stick a pin or resistor end or something into any of these holes, it'll have a nice tight connection to a piece of metal, and note that this whole big conductor will be one equipotential surface, as we learned in physics. So in the center, where we said the component buses are, this column down the center, that is a ravine for our dual inline packages, or our DIP packages, and that's what we'll use for our integrated circuits. So we'll put these, our DIP packages, across that DIP ravine. If we were going to wire an LED, a light-emitting diode, our circuit diagram, for example, would show 5 volts tied to this side of the diode, and the negative side of the diode pulled down through a resistor, and then we have a switch pulling that to ground. So when this switch is closed, we'd have the negative side of the diode at a lower voltage than the positive side of the diode, and the diode would turn on. So two different ways we could in fact wire that. If we had this vertical rail, which is flipped, so it's now horizontal, but this rail being our power, we could tie side of the diode to power, the proper side, and then through a resistor, noting that we don't have to now solder any of these wires together, we just stick them into the holes. And then we have a resistor, it jumps over the ravine, and then we have our push button, and this one side of our push button goes to the resistor, the other side of our push button goes to ground. We could also wire this such that we have, since these are not connected now vertically, this, however, is going to be connected here. That's where we pull up to the power, and here's how we pull our resistor through the push button. So just to show how we could use our breadboard. What we'll use in lab, however, is a protoboard. It's a PB503, which actually contains 6 breadboards. It has a power and ground rails. It has switches. It has regular flip switches on and off that are connected on, connected off. It also has no bounce switches. which one side is open, but they debounce, so you don't get any noise when you do the switch. It has LEDs for testing. It has a frequency generator that we can use for a clock, and a speaker that we could use also for testing. So an image of our protoboard. This section where we do our breadboarding, and it has all these other sections as well that support being able to test a circuit. For one, it is a powered board, so this wire, which we can't see, goes off. We plug that into an electrical outlet, and it'll take, your 120 volts AC, which is running at 60 hertz, and then using a transformer, it'll convert that, so it will provide 5 volts to our circuit, or it also has a transformer. We can adjust these voltages to plus and minus 15 volts, so we could use this to test analog circuits as well. We are just going to be using the 5-volt power. So let's go over some features of this protoboard. We said there's in fact 6 breadboards. The reason I say that is that there's 1, 2, 3, 4, 5, 6 different sections in this breadboard. If we want to connect these vertical rails for power and ground, then we actually literally have to put a little wire in here. So this shows in our leftmost 2 breadboards, we've connected the top breadboard and the bottom breadboard for the power and ground rails. They're not connected in these 2. If we wanted to connect them, we'd have to take wires and put them across there. So that's something you want to check to make sure when you're when you're trying to power and ground your integrated circuits, is your power and ground connected for the 6 different breadboards. Your power and ground rails, we see up here at the top, it shows the 5 volts. It shows a little wire that's going along this top row, which is also all connected together. That's a short circuit behind there. So 5 volts automatically goes to there once you turn the switch on, and ground automatically goes along this 4th row down here once you turn the switch on. So if we want to take this power and ground rail and bring it to our protoboards, we have to wire it down there. So we want to make sure we get them to all our rails. So I like to do power on the outside and ground on the inside, so your ground is always closest to the circuit. There's no, on our protoboard, there's no red or blue rail. So this is what this shows. Power on the outside rail, ground on the inside rail, and we're going to bring wires. You want to make sure that you have your wires connected from the ground rail to your ground column on each of your protoboards. Power 5 volts to the 5-volt rail on each of your protoboards, and you should use red and black wires for doing that. We also have switches to be able to provide inputs. Those switches, 8 toggle switches right down here. Switch 1 through switch 8 as they're labeled. You can have them set at 5 volts, or you could have them set at plus V. So we want to make sure we are using this 5 volts. We want to make sure it's to 5 volts here. And that's so this switch here, make sure that's flipped up. The switch to the left is set to 5 volts. If you run plus V, that could be whatever you have that setting to, but 15 volts to one of our 5-volt integrated circuits could burn the circuit, and it will be no longer useful. So for each of these switches, you have 2 options where you could pull a wire from. If you take a wire and pull it out here, then you can take switch 1 and switch 2 from up above, and you have our connection. We have 2 debounce switches. These are the 2 debounce switches here. And those, however, have to be pulled up. We'll use these also when we're trying to toggle a clock. We don't want to have any noise on a clock. So when we use these, one side of the switch has to be pulled to 5 volts. So we take one side of the switch through a 1 kilo ohm resistor, put that to 5 volts. The other side is where we'll get our signal from. We see there's an NC and an NO. There's 4 options to grab from the normally connected, 4 options to pull from the normally open. Normally connected, it means it's normally connected to ground. This is the ground symbol for the protoboard ground. This is our earth ground symbol. So normally connected to ground, if you push it, then it's going to be open and it'll be pulled up to 5 volts. If it's not pushed, then it'll be connected to ground. Normally open, when it's unpushed, it'll be at 5 volts. If you push the switch, it'll be connected to ground. So we'll use those. We got to make sure that you have your 1 kilo ohm resistor in place. Our frequency generator inputs, those are over here. Frequency generator, what you want to make sure there is that what we will use is TTL. TTL is what we'll use for our digital clock. If you pull from any of these others, you'll get a sine wave that goes plus and minus some voltage, or a triangle wave, or a square wave, which is not a clock. We want to go from 0 volts to 5 volts. So let's talk about some wiring standards. When possible, we'll use wire colors for different types of signals. Black we'll use for ground, red we'll use for power, and we'll use other colors for various signals. We want to have nice clean wiring. Examples of nice clean wiring: we never have a wire jump over our IC. It will be easiest to do that. However, once you end up with an error, it's very difficult to fix it when your wires are going across the top of your integrated circuit. So clean wiring is going to make your debugging much easier. It'll make your circuits much more robust. We're only going to insert components and wires into the breadboard when the power is disconnected. We're going to wire, we're going to check twice, and then we'll turn the power on. Make sure you never reverse the power in the ground. This is a very common mistake, and it's a mistake that can burn your ICs. Most chips will expect 5 volts. More than that will destroy the chips, so we have to be careful since our protoboard has a plus or minus 15 volt supply. We're taking care of our integrated circuits. We're going to use insertion and extraction tools. We're not going to use our fingers. That will bend the pins. So you want to minimize your contact with the pins. Additionally, static electricity can destroy the chip, so often used as wrist straps to ground yourself to help you be more careful, so that the static electricity doesn't burn the chip. An example of an integrated circuit: this is an AND gate, a 7408. All integrated circuits have a little, either a notch at the top or a dot that shows where your pin 1 is. The numbering goes 1, 2, 3, 4, 5, 6, 7, and then it goes down along the left and up along the right. If we had a 16-pin chip, it'd go to 8, and then 9 up to 16. For all our logic gates, pin 14 is power and pin 7 is ground. That's the same for all the logic gates. It's not the same for all integrated circuits, but it is true for all of our logic gates that we'll be using. So if we want to give an input a constant input, how do we configure the chip to do that? If we want a constant 0, we can just connect it to ground. If we want a constant logic 1, then we need to use a pull-up resistor to 5 volts. So we can use about a 10 kilo ohm resistor, pull that up to 5 volts instead of directly to 5 volts. For TTL family, the supply is 5 volts plus or minus a quarter volt. It must be very smooth. A regulated supply is best. Our protoboard will work just fine. In addition to normal supplying smoothing, a 1.1 microfarad capacitor can be connected across the supply near the integrated circuit to remove spikes as it switches from one state to the other. This is going to be important if you're making a big breadboarding a big circuit. For most of our circuits, we won't need to do this initially. For TTL, it's important to know that the inputs float high to logic 1 if unconnected. We can't really rely on this, so we want all unused inputs to an integrated circuit we should tie to ground or tie to well, typically what you do is tie them to ground. If you have an open circuit, it'll tend to float up to logic 1. So if you have an error in your circuit, it's like, oh, it's working now, but then it seems like it's not working, it's likely what you have is an input that's not connected, that you want it to be logic 1, but it's just floating to logic 1. Or it works when it's supposed to be logic 1. It doesn't work when it's supposed to be logic 0 because it's not actually ever being pulled down. So we should be aware of that with our TTL. Outputs can sync up to 16 milliamps. That's enough to light an LED, but they can source only about 2 milliamps. So to switch larger currents, you'll have to connect to a transistor. The fan out for a TTL gate is up to 10 for a 74 LS series, but it's more for if we're trying to drive CMOS. We do have to be careful, however, connecting LS series to the HCT series. And then we show propagation delay and frequency and power consumption for the TTL family. For the HC and HCT family, the HC supply can be from 2 to 6 volts. So these fluctuations are tolerated, whereas the HCT family, it has a higher toleration than the LS. It can be 5 volts plus or minus 0.5. These inputs have a very high impedance, or a very high resistance. It's good because it means they will not affect the part of the circuit where they're connected. However, it also means if they're not connected, they can easily pick up electrical noise, and they can rapidly change between high and low states and create more noise. So we want to make sure, it's even more important with HCT or HC circuits, that our unused inputs are tied low. These outputs can source and sink a little bit more. Source and sink about 4 milliamps, and again, if we want more, then we need to connect to a transistor. So let's talk about our open collector outputs. Open collector outputs can sink current, but they cannot source current. That's an open collector is our push buttons. So that's why we have to pull them up. So normally connected, it's normally connected to ground. When we push the button, it would be, well, this would actually be an example of normally open. It's normally open, so that would be tied to 5 volts. When we push the button and this switch becomes closed, now it's tied to ground. They only source or sink. They don't do both, the open collector outputs. Wiring procedures that we're going to suggest here, it's going to be important. Power and ground are connected to the vertical buses. Make sure that has happened first. Insert your primary components, and then insert your wires for power and ground for those components. And then you add the signals and remaining components and test incrementally. So at each of these steps, do a check and make sure that those are done. It's, the more careful you are initially in wiring your circuit, it's much easier to do that and take more time there than to debug. Your debugging techniques that we have, we'll use a multimeter, and we'll use voltage mode to check levels. We'll use continuity mode. It's another mode of the multimeter. We can just confirm connections, but we don't do that with the power turned on. We could also use an oscilloscope to view the voltage as a function of time on 2 channels. So our debugging techniques, we should test incrementally again and test intermediate sub-circuits. Our lab procedures, put your coats and backpacks and external material in the back of the lab so the workbench is clean of clutter. Food and drinks are not allowed in the lab. Try to eat prior to class or eat quickly between class and lab. Any approved food or drink must be kept by the sink. Clean your workspace first, then get your protoboard, get your wire kit, and get 1 fluke multimeter per bench. Retrieve the components you'll need for lab. Each bench should have 1 fluke multimeter and 1 oscilloscope for debugging. Each student will have to build and test their own circuit. I encourage that you work together, but each student will have to build and test their own circuit. Verification by the student must be observed by the professor, and be prepared to explain your verification procedure and your circuit itself as you demonstrate. Lab procedures, again, always check your wiring before you power your circuit, especially power and ground. When removing any chips from the breadboards, make sure your power is off for one, and use the appropriate tools, not your fingers. If you do break something, please report it. Don't just put it away. Return all your components in process of lab cleanup. If components are dead, put them in the dead component bin. Don't put them back in the good component bin. And store your protoboard and your wire kit in your drawer. Before leaving lab, make sure to clean your workspace. Put all your cables and components and breadboard away. It should be a lot of fun. Lab should be a lot of fun. I hope that we learn a lot and enjoy ourselves, work together, but everybody does their own circuits in lab. And away we go.